We'll begin our afternoon talks. We're going to be talking about AI revolutions in academia. And our first speaker today is going to be Markus Eberl, who's going to be speaking on machine learning and its application in his area of research. He's an associate professor in the Department of Anthropology, but he's an anthropological archaeologist. So he'll actually be talking a little bit more about archaeology. And really, one of the things I'll point out is that Markus and his lab have been really fast adopters of cutting-edge machine learning and now deep learning for use in research and in a field that had never seen this before. So it's tremendously exciting both to see this introduction into an area that had not benefited from it before, but it's also even exciting seeing your students and your postdoc adopt these tools and become so proficient that they are now writing and coding and getting published using these techniques. So, Markus Eberl.
Good afternoon, and I have to excuse myself for my voice. I'm still recovering from a sore throat. But yes, I deliberately put the et al. Here at the list of authors because I wouldn't be here without the help of Jesse, Charo, Abby, who are of course here, and their students. And that's really a key takeaway. I mean, this was an amazing experience. And also I put up this photo of myself taken quite a few years back when I was doing like traditional archaeology, because working with the DSI really made me realize how much my understanding of my own role as a scientist has been changing over the last years. And that's, of course, a story that I will tell in the following slides. So what I'm doing is basically, you see it in the title, Going Small for Big Data. To explain that a little bit, you see here a painting by Kiriko of, like, I guess, the traditional understanding of archaeology. You think about big buildings, pyramids, famous artifacts, the gold mask of Tutankhamun or something like that. The problem with all of that is, I mean, it creates, of course, amazing stories or narratives, if you will. And of course, media love to have these types of stories. But if you look at that from a scientific, especially statistical perspectives, our sample sizes are often woefully small. And archaeologists realized that, and over the last decade or so, people have been trying to implement big data approaches. I mean, LiDAR is one of these fields that are really coming out big right now. I'm taking a really different approach to that by basically looking the things, human-made things that are too small to be manipulated. And specifically, I will talk today about microscopic artifacts that I collect and my collaborators collect in soil samples that we analyze for human activities, where we try to understand past human worlds from these tiny or invisible artifacts, if you will. And big data really comes into play, as I'll explain in the following slides. So just to explain a little bit, why do I study that? Why do my students study that? I work in an area in modern Guatemala. I'll actually be going back in about 4 weeks from now, where the ancient Maya really made most of their tools from stone. So they didn't really implement metals. They weren't really available as ores in this area. So they mostly used stone tools. And obviously they had stone knappers to make all these tools that you see here on the upper right that are often shown in museums. What many scholars have realized over the past decades is that, of course, stoneworking creates very sharp debris. I don't know if any of you ever worked with volcanic glass or similar stones. These are actually super sharp. And what people realized is that ancient stone knappers, of course, knew that, and they removed all the debris from their workshops. Specifically, I mean, you see here on the lower right, like a drawing of a house of a modern stone knapper who explained to the archaeologist who inquired that, yes, I mean, he didn't want his kids to step across his workshop because, I mean, this would be way too dangerous. And he took all the debris away. And so basically, our understanding of where stone tools have been produced in the past is very limited because simply the workshops are cleaned out and there's no evidence except, and this is where I come in, all the tiniest fragments that are about like less than 6 millimeters. And so I'm interested in looking in these tiny fragments. And if you, to give you an idea, on the right, you see a modern recreation of a stone tool with all the debris that this making of the stone tool created, that we carefully collected. And again, there are multiple techniques involved. And I mean, for the detail for this presentations, they are not too important, but basically what makes it fascinating for me is that we have these ancient stone knappers, and we also have many modern stone knappers who recreate these ancient stone tools. And if you ever go to state fairs, you probably encounter them because they are really, they sell their arrowheads and similar things even nowadays. And what I did, and this is then the interesting part, I mean, I started off to look into these these debris, the microdebitage. Well, I mean, you can see it almost 20 years ago. I mean, you see me here while I was writing my dissertation. And up until about 2 years ago, this was a completely manual approach, meaning that archaeologists would collect soil samples, like the one that you see here on the upper right. They would look then for these tiny stone debris in these soil samples. And you probably, if you look at that, you can probably already guess the problem, because looking through a microscope for hours at end at literally hundreds of thousands of particles is basically exhausting. I mean, and this is where then the critique comes in my discipline, where people basically said, well, this type of technique, this analysis is basically useless. It's subjective. People don't really specify what are the criteria that they're looking at. How do you, I think, actually identify microdebitage? How do you do that over hours looking at the microscope? So this was another thing that I set aside, and literally now in my lab, I have like this box and others where I just labeled it, like you see it here. These are soil samples that I collected 21 years ago and basically never did anything with them, because I was like, this type of analysis doesn't really work for me, and I can't really produce any objective study. And what I'm doing now, and this is where the DSI really comes in, is developing a new approach that combines these three different aspects, and I'll explain them quickly. So on the one hand, would be the dynamic image particle analysis. So Vanderbilt helped me to obtain a specific particle analyzer that you see here on this photo. And this underlying principle, how it works, is actually very simple. You have this funnel on the top left part of this machine. You pour in basically anything free-flowing dry particles. They fall from this chute that you see here on the upper right. And here in the right part of this chassis is a video camera that literally takes a video of each particle that falls by. And then you have software that extracts photos of each particle as it falls down and then measures each particle. And this is then where the machine learning comes in a minute. Now, I also use then experimental archaeology to know what I'm looking for. So I'll explain that in a minute. And then most importantly, and this is where I've been working over the past 2 years with the DSI, I use multivariate statistics and machine learning algorithms to analyze this data for particles of interest. Now, just to give you an idea why I'm doing, or why I'm really looked for help with Jesse and Charot, what I realized is when I started to pour in the first samples into this particle analyzer is that literally I get millions of particles. I mean, what you see here on the upper right are the individual photos that are extracted from each particle. So each row corresponds to one particle. And normally you get about 6-7 photos from each particle as it tumbles down. So you get 3-dimensional information from these photos. And the software then measures for each particle about 40 variables. So you see here the output, the spreadsheet output on the lower right. And you can now guess, I mean, if you just put the, think about the numbers involved. I mean, samples, I now limit them approximately to 200 to 300,000 particles to not overwhelm the workstation. And I get probably from each sample about 10 million data points. So you can quickly see that I'm getting quickly overwhelmed with data. But it's fascinating for me because, as I'll explain in a minute, machine learning and statistics really help me to make sense of this data in a way that previously was completely impossible. Now, just to give you an idea what I'm looking for and how this looks like, I gave you photos of the microdebitage a few slides ago. The particle analyzer, the photos are only grayscale. And you see here on the top, the lower left, in the top row, particles of microdebitage. So these are the little debris from stone napping. And for comparison, in the lower row at the bottom, you see regular soil particles. So this could be sand kernels and little plant sticks and whatnot. And looking at that, I mean, you can probably already see, okay, there's a difference that we can capture. And of course, this is then where it becomes interesting. How can we capture that? How can we quantify these differences? As I mentioned, I mean, we started off with the spreadsheet output. So this is one just like a screenshot that I captured. And probably, and this is what I find fascinating about the application of AI. As a human, I can look at these numbers and I have really no clue what is going on. I mean, this is like, trying to get a pattern out of these numbers. This is really impossible. I mean, these are literally just millions of data points. And this is really where I realized, these are like where I'm as a human being overwhelmed to look at these numbers and trying to make sense of them. And this is, of course, then one aspect that statistics really helps me to make sense of it. And now also machine learning algorithms. And just to add, of course, one point, I mean, of course, when we talk about machine learning algorithms, we need to know how do we train the data? I mean, what is the basis that we know, oh, this is microdebitage or something else? And in this case, this is where the experimental part comes in. You see here like a stone napper, Mike McBride, a good friend of mine with whom I'm working. And so I do experiments with modern stone nappers and other craft specialists. I'll explain that in a few slides. Where they recreate stone tools and we collect the entire debris that they create. And basically, they use traditional resources. So I bring back like obsidian from well-known ancient sources to Nashville. They use these nodules to make the tools. They also use traditional tools, like you see here on the upper right, like antlers from deer to make the stone tools in the best way we know how the ancient stone nappers did it. And as I said, we collect the debris that they produce and use then this debris to train the machine learning algorithms, because we know this is microdebitage. And now we then we ask them to look for the same debris in actual soil samples to identify potential microdebitage. And what we are doing is, and as I said, we started about 2 years ago. I think Jesse is like 2.5 years ago. And Data Science Institute, we did multiple sprint sessions. And now the first results are coming out, literally. I mean, like the advances in archaeological practice has our article just in press. So I can share a few results where we used, in this specific case, we used the software, the spreadsheet output. We used a very limited sample, as I now realize, with you see about 5,000 data points and 80,000 like soil data points. And we compared 4 different machine learning algorithms. So we have a naive Bayes, GlimNet, random forest, XGBoost. And you see here the confusion matrices on the lower right that actually, I mean, it's actually really interesting for me that not all of these machine learning algorithms were similarly good in identifying a microdebitage. And in this specific article, we conclude that in our case, for this specific case study, the random forest model is actually the best performing algorithms. So this is also like just to reflect on machine learning from a scientific perspective. I mean, it's not like this cure-all phenomenon where you just say, oh, AI, and this will help me solve all of my problems. I mean, I realized working with Charo, Jesse, Abby, you have to talk about the specific algorithms, how they perform, and you see then still really great differences that I think the general public is not really aware of. And that's probably another topic that we can discuss at a different occasion. Now, the goal of this type of analysis, what I hope to do is what you see here. I mean, like this idea of reestablishing a type of analysis that has been really seen as impossible or impenetrable in the past. And you see here a few of the articles that have come out, that are coming out. And again, with the help of a DSI, we are also moving into the latest visual or the analysis of the visual outcome, the different photos produced by the particle analyzer. Where we started off like 2 years ago with the models, specifically convolutional neural networks offered at Fast AI. And I remember like Jesse asked me for the data to include it in one of his workshops, like exactly probably 2 years ago. And he emailed me like the next morning, like he was completely astonished. Like this is impossible, like this Fast AI model without any training. I think you didn't even change the parameters. It already classified like 99% of all particles correctly. So this was like really like for me, like, wow, this is impossible. And we then really spent more time rerunning, adjusting the model. And it's actually really it's fascinating for me to see what deep learning, in this case, like CNNs can do for my discipline and really change my perspective on how I can do archaeology. And just to bring it back to the particulars, suddenly with this type of data at hand, I can offer like an objective approach. You know, I can talk about what are objective ways to classify microdebitage. And more importantly, I can now move into large samples. I mean, literally, I mean, now I'm more in a position to limit sample sizes because I get the workstation, not me. I mean, the workstation gets overwhelmed with the data, and I'm no longer really as much confined as a traditional archaeology. Now, just to give you like an idea, what can we learn from this type of application of machine learning as a tool? So what you see here on the upper right is Rebecca Estrada, my current graduate student. So she's, for example, interested in gender differences. So this is, again, an interesting aspect. If you ever go to stone napping or nap-ins, as they're called here in Tennessee, you will be always surprised that these are mostly middle-aged to elderly men who sit there napping. And you always wonder, I mean, was that the same thing in the past, you know, that only males would nap stone? And Rebecca is actually interested in that question, you know, can we identify gender differences among stone nappers? So she has found, I think so far, 2 female stone nappers who gave her samples or debris of their work. And so she's now interested in studying these experimental samples for gender differences. And now she's applying that to soil samples that she collects at the ancient Maya site of Tzikinsakan, where I'm currently working, to see whether we can understand who was actually involved in stone napping in the past. Were these just males who did the stone napping? Were there also women involved, or even like children or others? The other case that you see here at the bottom is Amy Reed. She's an undergraduate student here at Vanderbilt. She's writing right now her honors thesis. And you see here her on the main plaza of Tzikinsakan, or well, one of the largest plazas of Tzikinsakan on the lower part, where she has collected about 550 soil samples from the entire plaza. And her goal is to understand how this plaza was used in ancient times, and specifically whether stone napping took place on the plaza. There's historical evidence that stone nappers literally napped for customers in major market places. But again, so far we have no archaeological or verifiable evidence for that. And so now she's looking for microdebitage in this huge plaza. And what you see here on the lower right, and this was actually more the fun photo. I don't know whether she's attending today's talk. I mean, we also had a howler monkey who unfortunately was killed in a fight, and she was like just gleaning over that howler monkey while she was collecting her soil samples. So there is also like this fun part of archaeology that shouldn't get lost in the digital world of machine learning. But yes, I mean, right now, hopefully right now, she's just finishing her honors thesis and hand that in to defend it. Now, also to give you another idea of what I'm doing, again, continuing the collaboration with the Data Science Institute, we obtained funding from the National Endowment for the Humanities to move beyond lithic microdebitage into ancient mortars. So in this specific case, we have a similar idea. Can we identify the different components that ancient builders used to build their buildings? And specifically, we use samples from an ancient site called Caesarea in modern Israel, which is famous because it was founded by King Herod the Great of biblical fame more than 2,000 years ago. It was occupied more than about 1,300 years until the Crusaders came and were then evicted from the city. And the specific interest that we have here is to understand the different ancient builders. So we have Jewish, ancient Roman engineers, we have early Byzantine builders, we have Arab builders who left stone buildings across the site. And of course, we have the Crusaders who also built like the fortification of Caesarea. And what we are interested in is, again, a question that could not be answered until this project. Did people actually use the same types of mortars for their buildings? Did they have like specific recipes that how they would mix the mortars? Then another aspect would be, did they exchange knowledge across these different cultures? Or did everybody just work within the blinders of culture and not look at builders that came before him or her, or other builders who were working elsewhere? Questions that could not be answered in any objective way. And what we are doing, and actually continuing to do this year, is to collect different mortar samples from Caesarea, and Abby is right now heading the sprint meetings. So where we used in the fall CNNs, convolutional neural networks, to analyze at least the experimental samples of different mortar constituents to see whether we can pick out and identify these different constituents. And what is still missing is to see how well it does when we apply it to actual archaeological samples. This semester, literally as we speak, we are applying transformer models to the same problem to see whether there's any difference in how they perform. So far, I think, and Abby, you may correct me, it's about the same. I think like with the CNNs, we're about at 80% recognition rate. With the transformers, we go about like right now still at 82, but we're trying to improve that. But the key part is, I mean, we're really working, and this is work in progress that we are also just writing up and presenting elsewhere. So this is here like a little bit of a conclusion for me here. What I'm doing is literally just like a new way of doing archaeology by integrating AI into and applying it to problems that previously my colleagues have deemed to be unsolvable or even impenetrable. And that's what makes it really fascinating for me, to really be able to do some objective analysis that previously was impossible for me. A key part that is also that I would like to stress are these different analytical approaches. So, I mean, I spoke a little bit about the visual analysis, the different algorithms that we applied, but in addition, we also use multivariate statistics to make sense of the data. So it's also, again, the question came up earlier today, can I trust the outcome of a specific algorithm? And at least I'm now more in the position of, well, I mean, I would like to see, if I apply like a quadratic discriminant analyzer, do I get the same results or do they differ? And that's then where it becomes really interesting for me as a scientist to compare these different outcomes. And of course, now I'm also in the position to move into the analysis no longer of just like a handful of samples, but literally hundreds. And that makes it really interesting because suddenly I can answer questions on a much larger scale than previously. And that's, of course, for archaeology, something invaluable. So this is a little bit the bright future that at least I foresee for my discipline, and I hope that this catches on. As I said, like this talk wouldn't be possible without the invaluable help of the Data Science Institute. Like, again, just a shout out to Jesse, Charo, Abby, because they're here, but then so many of the students really provided really important feedback for me and helped me to grow as an archaeologist. Then also like here, the digital humanities, who actually Mickey was the one who first pointed me to Jesse to say, oh, you should talk to this person. He knows how to help you. And as I see, I mean, Vanderbilt really gave me a lot of funding in addition to the National Endowment for the Humanities. So thank you all, and I'll be happy to answer questions. Annie, up.
Thanks. Mine's kind of specific to one of the studies you're talking about your grad student doing, finding if there were gender differences between the stone nappers.
Mm-hmm.
In training data sets, I'm assuming taken from like local stone nappers, was there actually a discernible difference between gender?
I mean, you know, she's still in the, I mean, she's right now just preparing for a comps, I should say. So there's like a tense moment where I shouldn't breach the larger topic of her thesis. But so far, like the preliminary studies that she did, she was able to show us, look at differences that, you know, samples that she collected from male stone nappers seem to differ from the ones that she got from females. So I hope that this, you know, will remain as she goes on. But yeah, I mean, it's like, so I find it fascinating approach to really look at this.
Maybe two questions. One is just fascinating work that you're doing. Have you looked at, are there native peoples in the area that do stone napping where you can collect samples from?
Unfortunately, not many more. I mean, I showed you like here at the very beginning, like one of the studies that have been done like in the 1980s on the lower right. So there are like so-called Lacandon Maya who still were stone nappers. But this is one of the issues, like stone napping as a skill is no longer valued. Yeah. I mean, this is really like where modernization really took over. I mean, people just use stone knives and, you know, metal knives, and it's kind of like stone napping. Why? But the interesting part is also like some people, native people, rediscover the roots. So it may change in the future where they suddenly realize, oh wait, this is actually a skill that we really mastered hundreds of years ago and we should go back. But yeah, unfortunately, it really died out in the 1980s.
It's easy to imagine that the stature and musculature of the peoples doing the napping would change the flakes. But so that would be interesting. Second question, you had a one-liner, I think in your last slide, about overcoming peer criticism. Mm-hmm. Would you address how you did that?
Oh, no, I mean, well, I mean, so this is the thing. I mean, and I was like in touch with Jesse whenever we get like when we submitted the articles to our peer-reviewed journals. And what is fascinating for me is that my peers openly admit, you know, if I would have seen this paper without the data that you have and the machine learning approach, I would have outright rejected it. Literally in the sense, you know, like this was an approach that was basically discredited like 20 years ago. And that's the fascinating, I mean, to the point that one of the reviewers even unrevealed himself, said, you know, this is really interesting and could we collaborate on that? And so that's what I mean, like, you know, that this specific way of doing archaeology was completely discredited. And I would agree personally. I mean, literally, I tried to do it myself this way, like with a microscope, and, you know, I couldn't see how you could do it objectively. And this is what basically I'm up against, you know, where peers say, you know, this is not a valid approach, but, you know, and then they suddenly say, oh, well, this could work. And then, you know, I mean, at least so far, you know, they have been positive about getting our articles published.
I found it interesting that we ended on stone napping kind of dying out or becoming more of an esoteric trade as we're talking about the evolution of technology and how some things replace other things and become obsolete. I'm just thinking about the meta of all that. What is it about the ones that still persevere? Like, why are they still doing it? And what is the evolution? What does that mean for what you're doing? We're doing why we're here.
And that's thank you for bringing up this meta level. I mean, again, it's like this interesting relationship that they have to the modern world. Like specifically, they work mostly for tourism. So like you would, if you, I mean, so I work in Guatemala. If you go to tourist-oriented markets there, you will have stone knappers who make like little bifaces for tourist use. But that's really like the extent of it. Like, they produce for the modern globalized market, and it's no longer really for their own personal utilitarian use. And then that's again, interesting. And this is like another aspect for me as archaeologist, working with local peoples and seeing how they relate to the technologies and where they often feel overwhelmed with like what they see happening in the northern hemisphere in the global north versus what they can do at home. So.
Just to comment on what you were saying earlier about the peer review, the skepticism, and that subjective element. It's a comment, not a question. It struck me that we were having a conversation earlier about radiologists and what AI is doing in the field of reading, radio images in medicine. What seems, it sounds like there's a similar thing happening. You have the human working by themselves. There are problems. You have the AI working by itself. There are other problems of reliability, but you get a qualitatively higher level if you have humans working with the AI. And that seems to be the case with radiology, and it seems also to be the case in what you're describing has taken it to a new level.
I mean, I would agree, at least for what I'm doing. I mean, I'm always trying to look back. I mean, I don't want to see AI as this black box where I just feed in massive data, and then at the end, I'm the consumer who just gets like a printout and say, oh, this is what I can publish. Again, like, for example, when I talk about the microdebitage characteristics, I mean, I ran the multivariate statistics to be also able to interpret the results that I get from the machine learning algorithms. So I think that's also important I mean, in a sense, I see myself in this position of wonder. On the one hand, AI enables me to do things that I could not have done like 10, 15 years ago. And at the same time, I'm kind of like this skepticist in the back of saying, is that something that I can really trust? And what do I need to do to verify the outcomes? And that's for me like a key part of integrating that into my work.